Well, I'm back in my office. You see, I don't have a big black screen behind me. I've got mountains now. We're in chapter 7. Chapter 7 is about describing the distributions of continuous random variables. Turns out what you need there is what's called the probability density function. And we'll finish this off by talking about normal density functions. And they'll close the loop on the empirical rule, which we will then step forward through coming up in the second half of this section. So we'll start off with this though. A probability density function, sometimes called PDFs, are also called density curves. Density curves are graphs where the graph can't be below the x-axis and the total area of the curve must be equal to 1. So you can draw whatever you would like here, as long as it stays above the axis. Any old shape you happen to like this. And then as long as this area is 1, then you've got a density curve. Well, there's a whole bunch of density curves people study. We're going to mostly look at the normal density curve, but I'll spend a little bit of time on the uniform density curve. And we'll do that first, just so you can see how it unfolds. So what density curves do is they look at the shape of the histogram when a lot of data is collected. And a lot of times when you do that, that shape becomes very predictable and a very smooth or even curve results. And then we can duplicate that curve mathematically and use it to compute probabilities, because that shape happens every time you sample from that kind of experiment. So one kind of experiment that you can do is involves what's called the uniform distribution. And the idea is to try to pick a number between 0 and 1, where every number is equally likely. And we can do that on the calculator. It has this feature on it. You go to math. I haven't been here for a while. Let's see what it is. Math, prob. It's got to be over here. Prob, sorry. And then there's rand. Oh, rand's right at the top. That's why I never see it. So then you go, there's all kinds of random things here. Random integer, random normal, random binomial, random no repeats. If you had some special thing you wanted to do, you could look up how to use those. But we're just using rand right now to create a random number between 0 and 1. So I'll activate that and I'll just hit enter. And then there it is. So that's 0.03480529, etc., like that. Now what's supposed to happen here is I get a decimal where all these digits here could be anything from 0 to 9 completely randomly. If I hit enter again, then I get 0.5673290052. We're going to keep doing that. Here's a tiny one, 0014431,957. We used this before to generate random numbers, but now we're using it to generate one random number, a number between 0 and 1. Here we go, 0.3249 stuff and stuff. Try it again, 0.66305 and stuff. And then 0.894386 and stuff like that. So what you can do then is collect a lot of these values and make a histogram. Hopefully that's what's coming. Let's just see what I've got here. So here's what they would look like if you did it 100 times. You get this kind of jaggedy thing. But an unusual thing happens. As you increase the number of observations, it doesn't happen very fast. There's 10,000. But you know what? You're supposed to be equally likely to be any of these numbers from 0 to 1. So these bars should basically be the same height. But of course they're not, because they're random. And so the randomness causes the jagginess. But as you increase the sample size, that randomness, percentage-wise anyway, tends to go away. And so what you get with a, there's a million observations, it seems clear as you increase the number of samples, the sample size over and higher and higher, that what's going to happen here is you're just going to get a rectangle like this. So the density curve is going to imitate that shape of a rectangle for large data sets. And then instead of using frequency on this axis, we're going to arrange the scale so the total area under the curve is 1. If the total area under the curve is 1, we think of that as the probability of all the possible values being 1. And then we can use geometry or something else, some other kinds of mathematics, to find the proportion of observations between two values. And we can also think of this as the probability a single observation falls in an interval. So the density curve will let us compute probabilities, not of specific values, because in these situations where you're getting numbers like this, you don't see the same number twice. You would have to wait quite a long time. So we think the chance of seeing any particular number is tiny, really theoretically 0, but of course that would be with infinitely many decimal places. So it doesn't make a lot of sense to hunt for how likely a number is. We hunt for how likely it is for a number to fall in a range of values. And that's what the density curve tells us. So we'll look at density curves for what are called uniform distributions. That means the height is constant, and you're equally likely to be any place between the two ends when you pick a random number. Here it is. Suppose x is equally likely to be any number in the interval a to b, like rand is between 0 and 1. Then we sketch out the density function to be this rectangle. So basically it's this height over a and b, and it's 0 outside here, like that. It's kind of hard to draw, so we usually put a dotted line here or something to indicate that that's the end of it, or maybe you don't put anything there at all. And then for the total area to be 1, the height times the width is the area. And so the width is b minus a, so that's 1 over b minus a times b minus a, and you get 1. That's why the height is 1 over b minus a. So if it was too wide, it'd be 1/2 tall. Here's an example. A density for being equally likely to be any number value between 5 and 10. And now we're thinking minutes late for class. This is you. You randomly come between 5 and 10 minutes late for class. You're equally likely to be any number between 5 and 10 minutes late. Here's what the density curve would look like for you. The width here would be 5. The height would be 1/5. And then if you want to say find the probability, you're between 7 and 9 minutes late. 7 is here, 9 is here, like that. You'd find the area under the curve between 7 and 9, like this. And so the height is 1/5, the width is 2. So 2 times 1/5 is 2/5, so 0.4. Probability is 0.4. So that's how density curves operate. Once you've got the curve figured out, you want to find the probability that the thing you're looking for falls between two values. You shade under the curve over the interval between the two values. So we did this here for a uniform density from between 5 and 10 minutes, whose height would then be 1/5 for the area to be 1. And then we asked, what about between 7 and 9? What's the chance of falling between 7 and 9 with that situation? We took the area under the curve, which is also a rectangle, width of 2, height is 1/5, area is 2 times 1/5. That's 0.4. 0.4 represents the probability. All right. So we'll move on to another kind of density function here. So it turns out, we'll see what it looks like. So we're back in here. So if we go rand, I don't know how to do this, plus, no, I guess I have to write it. Okay, I guess I have to do it. I don't know how this works. Because if you do rand plus rand, it might not work. Let's see if it works. So we go math, prob, rand, and then we go plus, and we go math. It's going to be hard to tell if this is working. Like that. So that might be giving us what we want. If it's giving me twice a random number, then the numbers will go from 0 to 2. If it's adding rand plus rand, they also go from 0 to 2. But you double a random number, then it's uniform, the same probability. So we'll just see what this looks like. So what we ought to see is numbers close to 1 lots of times, and numbers close to 0 or 2 pretty rarely. That seems to be happening. See those numbers? They're like 1.5, 1.0. If we did 2 times rand, like that, which I was wondering if we had that. We try running that. Then we ought to see, it's pretty hard to tell. It's pretty hard to tell the difference. I think those 0.5s didn't happen before. 0.25s aren't happening. So here we should be more likely to get big. There's a small number. I don't know. Rand plus rand might have been working. I can't tell. But I did it on my computer. So that's truly 2 random numbers as we started. And when you add a random number to another random number, then you get numbers from 0 to 2. But a surprising thing happens. First of all, it's kind of surprising. Most of the answers are close to 1. The center is 1 here. It's really hard to get something close to 0, really hard to get something close to 2. Because that way, to get those, both of those numbers have to be close to 0, or both of them close to 2. And getting it close to 0 is difficult, but getting 2 close to 0 is doubly difficult. And getting ones in the middle means I can get them if they're 2 about the same size, or 1 is big, 1 is small. There's lots of ways to get middle values, so it's easier to get them. And you get this triangular shape. It's convenient it's triangular for us because we can determine the density curve that we would use, because we need to take a triangle. And we know this width here is 2. And we want the area to be 1, and we know it's a triangle. And we know the area of a triangle is 1/2 the base times the height. So we're trying to figure out the height. 1/2 the base times the height is supposed to be 1. So the height here has to be 1 on that triangle. So that's the density, the corresponding density curve to this triangle. Once we figured out the shape, we arrange it so the area is 1. So it looks like this. Nice. You could get the equations of these lines if you needed to, but we're going to use geometry. We want to find the probability rand plus rand is between 0.5 and 1.5. So here's 0.5 here. Here's 1.5 there. So it's this shaded area here. But the total area is 1. So the sneaky way to get the area would be to look at the area of these skinny triangles on each side. They both are 1/2 by 1/2. And so if we added them together, here's an even sneakier way. 2 of them together would make a square like this. So I take this one and put it over here to get the total of the 2 of them. Then it'd be a square of sides 0.5. So 0.5 times 0.5 would be the area, was 0.25. And then this area here then is 0.75. And so the probability that rand plus rand lies between 0.5 and 1.5 is 0.75. So that's of interest mostly because you might wonder what happens if you add 2 random numbers together. And also of interest because the shape comes out to be a geometric shape, which makes it easier for us to figure out the areas under the curve, because we could just use geometry and triangles and similar triangles if we had to, but we found a way around it, which was nice. All right. So finally, after all that work has been done, we head back over to some notational issues. So when we've already seen this happen, when we had discrete random variables, we had the mean and standard deviation, wrote mu and sigma. But here things get a little more interesting because the way we create the density curves is by observing a lot of data and drawing a histogram. And so we naturally have to think about the mean and standard deviation of the data set and the mean of standard deviation that goes with this, continuous random variable. Unfortunately for us, the only way to get the mean and standard deviation that makes sense with continuous random variables is mostly to use calculus to do it, because you're having to find areas under curves to do it. So we can't actually do the nice things we did with discrete random variables and have formulas because they involve integral signs, but whatever, that's just where we are. But we can talk about the different notation that you use when you're looking at data and what density curves. And density curves really, this really says density curves, which really means random variables in general. So for data, we use x bar to represent the mean. For a giant data set, x bar and the density are probably almost the same number, but we use different notations. So x bar is something that changes from sample to sample, and mu is a characteristic of the distribution or the density curve that you're using to represent the distribution. And the median, we call it m mostly, and for density curves, there's not really a median. There is a median, but there's no standard notation. Sometimes over here, we'll use x with a little wiggle on top for median. Over here, I'm not sure. We don't usually worry about it, okay? And in the standard deviation settings, for data, we write s. And for density curves or random variables, we write sigma. So we have to be careful when we say standard deviation, that if we're looking at a density curve, we're going to compute the standard deviation in a way that we can't describe here. If we have data, we can compute the standard deviation because we have a formula. So there's a way to use the curve to get the standard deviation and the mean, which we're not doing, but there's some things you can do without using calculus. So one of them is estimating the mean. The mean can be estimated by where the shaded density curve would balance on the x-axis. And the median is the position that splits the shaded area in half. So if you have a triangular density function like this, you see the balance point would be in the middle of it there. So the mean is right there, it's at 1. And if you have a uniform density curve, then the balance point is somewhere in the center here like this. And so this one that goes from 5 to 10, the mean would be 7.5, halfway between 5 and 10. So that's somewhat useful. Gives you a way of guessing where the mean is. We'll get there. Here we go. I've lost where I was. It's here somewhere. Come back. It's at notation. Here we go. All right. And then for most densities, the standard deviation can only be computed using calculus. We keep saying calculus all the time. It's not that fancy, but it's needed. But you can estimate the standard deviation from the graph as the distance on each side of the mean that you have to go to include between 50 and 75% of the values. Usually the standard deviation is about that distance. And then for bell curves have a more distinct way of helping us guess the standard deviation, which we'll talk about in a minute. So that's coming up, and I'm going to close this particular session off, and because Zoom won't let you make long videos.